wireless communication.
Yeah, thank you, sir.
Good morning, sir. I welcome you for the FDP program on emerging technologies and wireless communication. Dear participants, today technical session will be handled by Dr. N. Satya Sai Srinivas from DRDO Uttarakhand. So I requesting to Suharika to introduce the today's speakers to participants.
Good morning, everyone. Dr. N. Sai Srinivas received BE and ME degrees under a dual degree integrated program in Electronics and Communication Engineering from Andhra University, Visakhapatnam in 2016. He received PhD degree in FPGA based digital VLSI system design from the National Institute of Technology, Puducherry, Karaikal in 2025. From 2016 to 2021, he was a research associate under a special manpower development program for chips to system design project funded by Ministry of Electronics and Information Technology, Government of India. With the Department of ECE NIT Puducherry since 2021, he is one of the founders and directors of ATRIEL Indian Private Limited, a startup company established and incubated at NIT Puducherry. Since 2024, he is a senior FPGA design engineering with the Keypoint Technology in Private Limited, Hyderabad, and working for Defense Electronics Application Laboratory, Defense Research and Development Organization, Dehradun. Additionally, he serves as an authorized intellectual property professional trainer under the National Intellectual Property Awareness Mission, an initiative by the Office of the Controller General of Patents. Designs and trademark marks under the Department of Promotion of Industry and Internal Trade, Ministry of Commerce and Industry, Government of India. Further, he serves as an ISEA ambassador under the Information Security and Education Awareness Program, an initiative by the Ministry of Electronics and Information Technology, Government of India. His research interest includes FPGA based digital VLSI system design, digital speech processing and machine learning. He has published several research papers in leading inter- international referred journals, conference and national book series. He has granted two patents to his credit. He was the reviewer for several referred international journals, including Microelectronics, Computer Speech and Language, Optic, International Journal of Speech Technology, and conferences. He has delivered invited talks in several national level seminars, webinars, and faculty development programs held at leading academic and research institute in India and international congress meetings held at abroad. He holds several he holds several international and national awards and recognitions, wherein he was a recipient of MathWorks Certified MATLAB Associate credential conferred by MathWorks in USA in 2015. AWSAR Award in 2019 conferred by the Department of Science and Technology, Government of India in 2020. Swadeshi Microprocessor Challenges Semi-Finalist Award conferred by Ministry of Electronics and Information Technology, Government of India in 2021. Best Design Award conferred in the design contest of the 26th International Symptoms on VLSI Design and Test by the Indian Institute of Technology, Jammu in 2022. International Travel Support Grant conferred by the Science and Engineering Research Board, Department of Science and Technology, Government of India in 2022. Thank you.
Sir, with this brief introduction, now we are hand over the session to you, sir. Please share the PPT and you can go ahead, sir.
Okay, sir. Thank you very much for a brief introduction. I hope I'm audible, right? So let me share my screen. Is my screen visible to everyone? Please confirm.
Yes, sir.
Okay, okay.
Yes, sir. Your screen is visible, sir.
Sir,
Yes,
make
sir.
it full screen, sir.
Full screen? Yeah, yeah. Just a minute. Now is it clear, right?
Yes, sir. Yes, sir.
Okay,
Sir.
okay.
Yes, sir.
Yeah, good morning to all the participants, both attending in online and offline. Welcome to today's session. Myself, Dr. Nittimi Satya Sai Srinivas. Today I'm going to. Hello.
Sir, go ahead, sir. Go ahead, sir.
Okay, okay. Sir, kindly turn off, mute your mics. Okay. So
Yes, sir.
today, today I'm going to present a session titled 5G Physical Layer Processing on FPGAs. So what are the key objectives of today's presentation? So the first objective is to demonstrate the implementation of 5G physical layer processing on FPGAs with a focused exploration of prototyping custom hardware architectures on FPGAs tailored for specific 5G physical layer components. The second objective is to provide a practical understanding of the complete industry standard design flow usually adopted in order to translate the system level specifications into efficient FPGA based hardware architecture designs. So in today's session, maybe we like 1.5 hour or to 2 hours, we may not be able to implement the entire 5G communication system, but the main agenda of this session would be focused on if at all, if there are any given specifications related to a 5G communication system, what is the framework that is usually adopted as per the industry standard in order to design right from the scratch and to get a full-fledged product, final finished product in terms of hardware implementation of a particular component in a 5G communication will be briefly demonstrated and illustrated in this session. So these are the two key objectives. And another main objective is I just want to focus on bridging the gap between the theoretical learning and the real world hardware design in order to enable the participants to gain some insights into how a 5G communication system is realized on FPGA. And at the end of the day, the key takeaways will be to encourage all the students, researchers, and faculty members to develop some innovative research projects in the areas of 5G wireless communication systems. So, by demonstrating how the academic knowledge in digital signal processing and digital design applies to modern 5G systems. Uh, and I also want to inspire the participants how to take up their ideas into a practical circuits being implemented on FPGA. This flow is more or related to be a generic standard, but we are using it for 5G communication system implementation. However, the same design flow what I'm going to deal with in the next 1 to 2 hours can also be adopted to realize hardware architectures on the FPGA platforms. So I'm just trying to make the seminar on presentation more generalized, and at the end just target it to some 5G communication system application uh, for in order to show all the participants how a traditional industry level based research and development takes place. So who are the targeted audience for this program? Obviously, the first one will be the faculties who are working in the areas of electronics and communication engineering on a broader perspective. And the second one will be the like research scholars who are working in the areas of maybe 5G wireless communication and FPGAs. And last but not the least, like ME, MTech and MS students and BE, BTech students who are working in within the broad areas of electronics and communication or within a focused areas of wireless communication and VLSI. So all these type of audience will be benefiting from this tutorial. So what are the prerequisites for attending this lecture? So I expect like the people, all the participants who are attending this session, both in offline and online, will have some basic understanding and working knowledge of digital signal processing, digital circuits and systems, and some concepts of digital communication and wireless communication, and hands-on experience in MATLAB programming, Verilog HDL programming, and experience with EDA tools like Xilinx Vivado and Xilinx FPGAs. So as the title suggests, it's like 5G physical layer processing on FPGAs. So from my end, I am going to show a demonstration of implementing a 5G communication system component on FPGA. So for that purpose, I am using Xilinx FPGA as my target device. And in order to carry out the design and implementation, I am using Xilinx Vivado software tool. These two things you'll be coming into more, we'll be getting into more details as the session moves on. So coming to what is the need for building communication systems using FPGAs and SoCs? Um, a- in today's modern world, as the technology is upgrading day to day, we see often huge advancements that are taking place very rapidly in a very short period of time. And in order to implement the systems, we generally adopt like ASICs, application specific integrated circuits. But getting an ASIC for the actual implementation or the actual system will be like time taking. That's why nowadays the use of FPGAs and system on chips SoCs are very rapidly used because of one main advantage, that is like rapid development. So these FPGAs and SoCs are readily available programmable integrated circuits wherein you can do some customization, you can implement your logics or algorithm and try to realize your own hardware out of it in less amount of time. In the conventional way, if you're looking for an ASIC manufacturing or fabrication, these things, so there is a large turnaround time with respect to the design and obtaining the IC at your vicinity. So the key advantage of using FPGAs is like rapid development. It enables quick validation of new algorithms and protocols before ASIC production. So real-time testing, it allows live system evaluation with real-world signals and conditions. And using of in SoCs, we have a part of FPGAs and a standalone processor. So by using FPGAs as a configurable logic, we can build our hardware, and by using the existing processor, we can develop some software applications. So technically we call it as hardware software co-design. So SoCs combine FPGA with processors. These two is a very good combination which enables flexible hardware acceleration and software control. So nowadays the term like SDR, like software defined radio, is very familiar. So we are incorporating customized hardware. On top of it, we are writing our own software in order to control our communication modules. So this is easily achievable, and by using the FPGAs or SoC which are available in the market. And moreover, FPGAs and SoCs are very cost effective. They reduce the research and development cost by avoiding expensive and time consuming chip fabrication cycles. So fabricating a chip maybe takes around like more than 1 year or even upon the scale of manufacturability. And even if you want to implement a single test chip, it also costs a very huge amount, like in the order of crores. But modern day FPGAs, like high end FPGAs, you can get it maybe like in between like 5 to 10 lakhs of amount. So it is very much cost effective when compared to application specific ICs. So we can easily get the readily available evaluation or development boards, and we can start building our circuits and prototype it and then implement. And after testing, you can also deploy it in real time applications. Another big advantage of using FPGAs and SoCs is like scalability. So designs can be you scaled or it can be modified easily to meet the changing requirements and changing standards. Actually, the currently the 5G and we are also entering into the 6G communication. All these communication standards are day to day getting updated, adapted. Uh, Standards are revised, standards are modified. So depending on the updates and changes in the standards, we should be able to replicate the same things in terms of the hardware. So in that case, the rate at which the standards and requirements are changing, if you want to incorporate the same things in terms of a hardware, using FPGAs and SoCs will try to help you in meeting the turnaround times. So these are some specific advantages of using FPGAs. Uh, this session is mainly focused on like 5G physical layer processing. So what is the significance of implementing 5G physical layer processing on FPGAs? So I have just briefly listed out. First one is like, as you see the generations of communication, we the transition from 1G to 5G. So mostly we talk about bandwidth, high data rate application, high speed of processing. As the generations upgrade from lower level to higher level, we see in updation, we see in the improvements in the quality of services, and we see in the high data rates that are being supported by the technology standard. So as the generation of communications progress, the speed of data transfer from source to destination is increasing very rapidly. And in order to support this high speed of processing, we need some circuits like hard in the form of a hardware which can support these high speed of data processing, data transfer features. So FPGAs comes into that picture, and as they support high speed processing, because 5G also requires ultra fast real time signal processing to handle massive high data rates. As about says like massive high data rates, we are dealing with huge amounts of data, and that huge amounts of data needs to be processed in less amount of time with very less latency. So that is possible by use of FPGAs when compared to the traditional general purpose processors. So you may also ask like why to use FPGA? I can use a processor instead of using an FPGA. So there are some particular advantages that comes with using an FPGA rather than a processor. So that is one is like high speed of processing. Second one is like the flexibility. These FPGAs, as I mentioned, it's a programmable hardware. It allows the end users to customize the hardware as per their requirements. Whereas in the general purpose processors, you don't have control on the hardware. The hardware is fixed, but whatever the end user tries to implement, he will only be making updates or changes at the software level, but at the underlying hardware that is fixed, and the performance is directly dependent on the hardware. So even though how much efficiently he writes a software code for any given application, the ultimate performance of the entire system depends upon the underlying hardware in case of the general purpose processors. But whereas in the terms of FPGA, the user has full controllability on the hardware architecture. He can make updations, changes. He can customize the hardware architecture as per the application requirements. So there is a lot of flexibility in using FPGAs. Another great advantage is like parallelism. So FPGA architectures support parallel processing, which is very much ideal in modern day communication systems like in 5G. And coming to low latency, it is essential for 5G use cases like autonomous driving, where milliseconds is also makes a huge impact and it also matters. So in order to have a low latency of processing, FPGAs comes into the picture. And energy efficiency, FPGAs optimize power consumption compared to general purpose processors for physical layer computations. So these are some key significances of FPGAs for using in 5G physical layer processing. So you must be getting a doubt. So what is an FPGA? I think everyone has a basic idea of what is an FPGA. So it is basically a semiconductor device that can be programmed and reconfigured after manufacturing. So it consists of an array of configurable logic blocks and interconnects that allow hardware functionality to be customized. It offers hardware level parallelism, enabling high speed and low latency processing. These FPGAs, as I said, these are widely used for prototyping and accelerating compute intensive tasks and real time processing. So these are some key differences between FPGAs and general purpose processors. So in terms of architecture, FPGAs reconfigurable hardware processor is a fixed hardware. Coming to the execution, FPGAs do support parallel processing, and whereas a processor is completely based on sequential processing and it's an instruction based, whereas an FPGA is like a custom data paths based. Coming to the flexibility, in FPGA, you can do programming at the hardware level. That means you can define your own hardware in order to meet the specific requirements of your application. Whereas in the processor, the programmer it is programmable only at the software level. And the underlying hardware remains the same. So whatever the application you will be developing, you will be developing at the software level only, and it will use the existing hardware in order to perform that. Whatever the predefined tasks. So performance wise, FPGAs have high throughput and low latency when compared to the general purpose processors, uh, and they are slower for parallel processing tasks. And use cases, FPGAs are used for real time and high compute intensive applications and tasks, whereas a processor, it's like general computing and multitasking. So here you won't be getting a compute intensive task feature because the processes tend to be little bit slow when compared to big data, huge data for processing. And power efficiency, more energy efficient for specific tasks, and the processor is like less efficient for specific workloads. These are some key differences. I think these all are already the students have gone through in their curriculum. So I just want to just brush up their knowledge. That's it. So coming to the FPGA design flow. So if you want to implement any hardware on FPGA for any specific functionality or so on and so forth, as per the industry standard, we do follow one specific sequence of operations. So that we call it as FPGA design flow. So it has nearly 10 to 11 steps as I have listed out in my PPT. So into this session, we will be addressing each and every design flow. I will be discussing all the flows in detail, and then we will follow the same design flow in order to prototype a 5G communication system on FPGA. So the first one is like the first and foremost step is like system specifications. So if someone asks you like I need so and so component to be implemented on FPGA, they will give you the specifications of that component. So what is that component? What is it about? And what are its inputs, what are its outputs, what the component, what is the component functionality, what it is supposed to do, each and every pinpointed details related to the specifications. So this is called in the first step we are the designer who is going to implement for adopt or follow this FPGA design flow will collect all the design specifications from the customer. So from there, he will analyze all the design requirements, and based on that, he will proceed to the next step. So in our system specification, today we are going to address one problem. As the title of our session is like 5G physical layer processing on FPGAs. So in physical layer processing, there are a pipeline of uh, operations that are being performed. There are a number of operations which are implemented in a pipelined operation in order to model the communication system. So we are in this less amount of time, we will be not able to implement the entire system on FPGAs. So for that purpose, I'm only considering one specific block. So now we will see what are the design specifications of that block. So allow me to update my screen. I'm just opening the block diagram of a typical 5G communication. This is how I think it is visible, right? So as I mentioned, it has a pipeline of operations that is being performed. Uh, this is basically a transmit chain. So again, at the receiver end, inverse of operations of all these inverse operations will be performed in order to retrieve the data which is being sent by the transmitter. So I'm not going into much details of each and every processing block. Why? Because it is out of scope of the current session. Uh, in this blocks, you can just I'm just uh, asking you to just pay a focus on a block number 7 that is called scrambling. So in today's session, we will be discussing on this particular block, the block number 7 that is called scrambling. In the transmitter chain, at the receiver chain, we have a descrambling. So that is an inverse operation of the scrambling. So that we will see in more detail in the later part of this session. So if you take this 5G communication system, this is a typical block diagram. You have many different versions of the block diagrams for 5G communication. I have taken this one. So just prior to the modulation, in any communication signal, if you have a message, we do modulate it and then we feed it to the RF front end and then we transmit it and we send the signal in the channel. And at the receiver end, again, the RF will pick the signal from the channel and does inverse operation and it does demodulation and then retrieves the message. So as per the 5G communication standards, whatever the data that you're feeding to a modulator, that is for modulation, we don't feed the data to the modulator for modulation purpose directly. Instead, we pass it to a operation called scrambling, and the output of the scrambling operation is the whatever the data we are getting, that is fed to the modulation. And in modulation, I think you are very much familiar about BPSK, QPSK, QAM. These are the modulations that are widely used. So before giving the original data to the modulator, we do pass it to a scrambler, and from the scrambler we take the data. That data is being fed to the modulator. These are the brief details. So now what we try to do is, given the data, how you will implement a scrambler circuit on FPGA to do a 5G physical layer processing, and how do you output the scrambled data. So we are just focusing on this block. So coming to this one, the first step is like design specifications, and our objective is like to design and implement scrambler on FPGA. So this in turn is nothing but this is a part of 5G physical layer processing. So we have seen in our FPGA design flow, that is like system specification. So we need to define the design requirements and functionality. So this is the design specification. So our, in a broader perspective, what our design specification is saying. So we need to design and implement a scrambler on an FPGA. For on an FPGA, yes. This demonstration will be illustrating like 5G physical layer processing on FPGAs. So now we need to know what is scrambler. So because we need to capture all the design requirements over here. So once we know what the scrambler will do, then we will be able to implement it on the FPGA. So let's see what is a scrambler. So here we just try to analyze the algorithm, because once we know this algorithm, we will be understanding what the scrambler is like. So as I mentioned, there are standards, right? So this scrambler is defined in a standard that is called as 3GPP TS 38.211. If the participants who are interested to know more details about the scrambler and the standards which are used for 5G, this is one particular standard, 3GPP TS 38.211 document. You can just go through this document. I am also telling with respect to this document. So in this document, in 5G, we have different types of channels, and each channel has its own standard for scrambling. For the illustration purpose, I am taking PDSCH. This is called as physical downlink shared channel. So as per for this type of a channel, the scrambling is defined as follows. So consider a code word that is Q. Actually, two code words like Q equal to 0 or 1 being transmitted as per the standard. In our case, we are only considering only one code word for transmission. So for one code word, Q is represented as 0. So we are going to transmit a code word, one code word, that is Q. the queue has a maximum of m bits. So the code word has m number of bits. Bits means like we have either zeros or ones. It's a sequence of zeros and ones. So in our design, I am considering my m bit to be 8, but this is not given in the standard. The standard says like the code word can have m number of bits, but I just want to implement some prototype on the FPGA, right? So for that purpose, I am considering m bits, m bits equal to 8. So say for example, like my code word is like 10101011. This is one type of 8-bit code word. So as I mentioned, my code word, this is one code word, right? So this is like LSB bit. This is like MSB bit. This is bit positions are like 0, 1, 2, so on up to 7. So these all are like individual bits, right? So these are represented as B of 0, B of 1, B of 2, so on, B of M bit minus 1. So 0, 1, 2 up to M bit is 8 minus 1, that is 7. So 0 to 7. Actually, in the documentation here, Q notation is also available, where Q denotes the number of code words. In our case, we are sending only one code word. So for that, in that case, Q is equals to 0. So if these are the bits, then you need to do scrambling, right? So this is your high level block diagram of a scrambler. Here you are giving your code word, that is B0, B1, so on, BM. And here you are getting the scrambled bits, that we call it as B0 bar, B1 bar, B2 bar, so on, BM bar. Now what is going inside the scrambler, that it is taking this input and transforming in this to this output. Now we try to understand what is the scrambler operation, how it is working. So as per the standard, that is the output of the scrambler, that is bi bar, say for example, is equals to bi, that is XOR with ci, where in this case I belongs to like 0 to 7, since we are taking 8-bit message. So this is the scrambler equation. So bi bar is nothing but the output of the scrambler, that is scrambled bit. Vi is called as the message bit. Ci is called the scrambling bit. The entire C we call it as scrambling sequence. So that means like we have a message bit and message data, and we have a scrambling sequence. We do a 1-to-1 XOR operation to get our scrambled data. Now I want to give an example. So our message bits like BI, say we have 1 0 1 0 1 0 1 1. So, and we have a scrambling sequence like 0 0 1 1 1 0 0 1. So what it says, like we need to do an XOR operation to get the scrambled data. So 1 0 1 0 0 0 1 1 0 0 1 1 1 1 0 0 0 0 1 0 1 1 1 0. So this is the scrambled sequence. So this is the original message. This is the scrambled message. This is the output of the scrambler. On the receiver side, you need to do descrambling. So in the descrambling side, again, you need to use, the receiver also needs to use the same scrambling sequence, whatever we have used at the transmitter. That is 0 0 1 1 1 0 0 1. Again, here also you need to perform an XOR operation to recover the original data. So 1 0 1 0 0 0 0 1 1 1 1 0 0 1 1 0 0 0 1 0 1 0 1 1. So 1 0 1 0 1 0 1 1. This is our original message that we have descrambled at the receiver end. So from this it is very clear, like we have one code word and we have a scrambling sequence. We do an XOR operation, we get the scrambled output. And at the receiver end, again we need to use the same scrambling sequence to get back your original message data. So this is the top level description, like how a scrambler works. So finally, the scrambler output BI bar is nothing but message bits XOR with scrambling bits. So this is our main equation. Now the thing is, like, how do we get the scrambling sequence? So the standard, what we are talking about, that is 3GPP TS 38.211. This is a standard. What does it say? It has some guidelines on how to generate the scrambling sequence, that is CI. So now let's see how to generate the CI. So to generate that CI, the standard says to use sorry to use PRBS generator. PRBS generator stands for pseudo random binary sequence generator. So we need to use a pseudo random binary sequence generator in order to generate our scrambling sequence CI that can be used by a scrambler in a 5G physical layer operation. So now we will see how to generate a pseudo random sequence. So in order to generate a pseudo random sequence, it is asking to consider two sequences, that is x1 and x2. x1 is of 31-bit length and x2 is also of 31 bit in length. Now what we are supposed to do? The scrambled sequence is being represented as C of n is equals to x1 of n plus some offset, that is nc, plus x2 of n plus some offset, that is nc. This plus is nothing but modulo 2 addition, that is equivalent to an XOR operation. So this is the equation. The scrambling sequence C of n is equals to x1 of n plus nc, x2 of n plus nc. Now what is this nc? Actually this is two sequences, right? X1 and x2. These are also called as gold sequences. By using these gold sequences, we will compute the scrambling sequence. Actually, this gold sequence exhibits some random property. The data within the sequence is random in nature. We will see how it is that random. Basically, we will come back to this final equation little bit later. So first one, that is x1 of n, right? Second sequence x2 of n. As I mentioned, it is a 31-bit sequence. This is also like 31-bit sequence. So what is the point is like first initialization. How do you initialize this sequence? So as per the standard says like in case of x1 of n, where n varies from 0 to 30, that is 31 bits, right? So x1 of 0 is initialized to 1 and x1 of from 1 to 30 are left as 0. This is a single bit 1, this is a single bit 0. So if we take like this is LSB, this is like MSB. The LSB bit, that is the 0th bit of the sequence, is 1, and the MSB bit, that is 30 to up to 1, 1, 2, 3, so on, all are zeros. Now the second one, x2 of n, this is also initialized. It's some random data. So how do we initialize x2 of n? So it has one particular specific requirement. As per the standard, it says like you need to initialize x2 of n with a c underscore init with this data, that is c initialization. This is one sequence. This is also like 31-bit sequence. And how do you get that c underscore init? There's a specific formula, that is n rnti into 2 to the power 15 plus q into 2 to the power 14 plus eta id. This is a formula. As you remember, since we are discussing only for one code word, a single code word, q is equals to 0, right? So if you substitute that one here, eta rnti into 2 to the power 15 plus 0 plus nid. So finally, C initialization, sorry, C initialization is equals to n rnti into 2 to the power 15 plus nid. This is the final equation. So here RNTI, what does this represents? It represents a radio network temporary identifier, and NID refers to network identifier. These are unique for each NR. NR stands for new radio, that is a mobile unit or a user equipment, or you can say it as anything. So based on this, the CNIT will be initialized, and this CNIT will be used in the X2 of n. So clear. So X1 of n is initialized like 0, 0, 0, 0, so on 0, 0, 0, 1, initialized with 1. X2 of n may be some random data, random 31-bit data. This network ID has one specific range, that is from 0 to 1023, and RNTI has specific range from 0 to 65,535. So the CN90 is like 31-bit data, so depending on that, the value will be calculated. It is like decimal data. CN90 is some decimal data. Say for example 4912536, maybe this some random data. This if you represent with 31-bit data in binary format like zeros and ones, you will get the X2 of n. These are like initial data, initial condition. This is not pure random, but we need a random sequence. At the end of the day, we need a random sequence, that is C, for that we call it as scrambling sequence, that we are constructing with x1 and x2. But as of now, we have just initialized x1 and x2. But this is not pure random. In order to get pure randomness, we need to perform some iterations. Hello? Yes, anyone is having any doubt? Okay, we need to perform some iterations in order to get randomness. So how do you perform the iterations? By using linear feedback shift register concept. So the iterations are defined by some recursive equations. that is x1 of n plus 31 is equals to x1 of n plus 3 XOR with x1 of n. Similarly, x2 of n plus 31 is equals to x2 of n plus 3 XOR with x2 of n plus 2 XOR with x2 of n plus 1 XOR with x2 of n. So these are the iterations that you need to perform. So if you remember, I told you, right, the final equation here, scrambling sequence C of n is equals to x1 of n plus nc XOR with x2 of n plus nc. So first we construct x1 and x2, we initialize it, and then we run this recursive equations. These are the recursive equations, right? By using linear feedback shift register hardware, we run this recursive equations up to how many clock cycles, like how many times, how many iterations, NC number of iterations, where NC is, as per the standard, it is equals to 1600, 1600. So 1600 times we run these iterations, and then after 1600 cycles, we start taking the data out from the shift register. After these all iterations, the data seems to be like random in nature. In order to get randomness, we do these many iterations. So this is simply straightforward. In case of an X1, we construct a linear feedback shift register. Like from 0 to 31. This is like LSB, this is like MSB. This we take it as output, and this is like input. As the equation says, n, you need n plus 3 and n, right? So n means the zeroth class. This is 0, 1, 2, 3, and this is a third part. Just a minute. Yeah, I have done it wrong. Yeah. So maybe this notation you can remove 0, 1, 2, 3, so on, 30, 29. So like this, you just tap the registers. This is the output. And from this part, the data goes like a feedback and enters. From the front, the data bit exists. After exiting, it undergoes XOR operation and then re-enters into the linear feedback shift register. So initially this cycle is performed up to 1600. After that, whatever the data is coming out from this position. Now that data bit is taken simultaneously, and it also goes into the feedback as well. So we start reading this line after 1600 clock cycles. This is for x1 of n. So we need to get, since we are considering an 8-bit 8-bit code word, we need 8-bit sequence, right? So after 1600 clock cycles, we start outputting 8 bits from x1 from this linear feedback shift register. Similarly, we have another linear feedback shift register, that is x2. So as per the x2, you can see 3, 2, 1, 0 are the taps. Maybe this one, 3, 0, 1, 2, 3. So 0, 1, 2, 3. Okay. One, three. Okay. This is x2. So these are the tabs. We have taken 0, 1, 2, and 3. We have fed back it. This is x2. This also, the cycle repeats for 1600 clock cycles, 1600 times. And then finally, whatever the data that is coming out from this location now, we take it and we construct x2 of n, that is 8 bits. So finally, as I told you earlier, as I mentioned earlier, C of n is nothing but x1 of n plus nc plus x2 of n plus nc. Here plus means like XOR. So we combine the x1 and x2 sequences to get the Cn sequence. And once we get the Cn sequence, we XOR with our message sequence to get the scrambled sequence. And the same scrambled sequence at the receiver end, we pass with the same scrambling sequence to get the original message bits. So this is the design description. So understanding of all the process is very important in the first step of the FPGA implementation, that is design specifications. So actually I have given lot of mathematical equations and I have just explained how the scrambling goes and how the module works in terms of mathematical model. So, and I also defined some constants, right? Like we have defined that x1 and x2 are 31-bit length. And for generating x2, we use some initialization sequence, that is RNTI into 2 power 15 plus NID. RNTI is network word radio, is nothing but radio network temporary identifier. It has a decimal value in between the range 0 to 65,535. We have to choose one specific value, that is user choice. Next one is NID, network identifier 0 to 1023. All these key information forms the basis of the design specification. So here we will do some constraining, like we will set few parameters while designing our hardware. So understanding all these things is very important as a first part of our design cycle, that is FPGA based design flow. The second one is like algorithm development. So once we are very much clear, like end to end, how to do this implementation, how to carry out and everything, then we start to implement this in the software level. First of all, in order to verify what we call that is as like proof of concept. This is all the entire concept. And we want to verify that we call it as proof of concept. So for this purpose, what we do like a MATLAB modeling. we implement all these equations and try to generate a pseudo random binary sequence, and we take some message sequence, do the XOR operation, find the computed uh, scrambled data sequence. So for that, we can use either MATLAB or C language or any Python or anything in order to get a complete idea of how the algorithm works. Once we have implemented in the simulation demo, then if the things are very much clear, then we can proceed to the next step. The next step starts to the real hardware implementation. So doing a software level simulation modeling of the concept is very much important. So we have completed the first two steps. We have acquired our design specifications. We have taken our design specifications, and then we we will do a MATLAB or a Python based or C level based implementation only to check how the functionality is. Once you do this development, we will get a clear idea like how to proceed to the next level, like hardware implementation. What are the things which we need to take care of? How do we start our hardware designing? Those all things, the picture becomes very much clear once you implement it in hardware. So first we understand the specifications, and then based on the specifications we try to develop some simulation model. After this, now we will proceed to the RTL designing. Actually, the MATLAB based C or Python based simulation model or algorithm development is out of scope of the current session. So this I am not discussing. Algorithm development, we assume like whatever the equations that we have discussed so far, these all things has been implemented in MATLAB, and then it has been validated, and we have understood very well what are the specifications to proceed further in hardware implementation. And next one is like now based on implementation.
Sir,
Now,
Sai sir,
yes, sir.
sir, can you give 10 minutes break, sir?
Yes, yes, sir. Sure. Actually, I
Sir,
am also planning to stop at this instant.
okay,
Okay.
okay. So
Just one
after,
minute.
yes,
Just 1 minute. So the next thing comes like RTL design, but writing a Verilog code and everything is also out of scope of this current tutorial. So what I will do is like I have already developed an RTL code. I have already developed a scrambler circuit. So based on that, now I will show how to proceed further in all these steps and do the FPGA implementation. That we will see maybe after like 5 to 10 minutes of break.
yes, sir. After 10 minutes again, we will rejoin, sir.
Okay, okay, sir.
Okay, sir. Okay.